Okay, so is everyone able to hear me? Okay, perfect. So tonight we're going to be working through a final exam. And could you possibly do the 2013 one? Don't think I have that one, but I think, just a second. Just a second. Checking my videos, because I'm pretty sure. So which one did he wanted? He wanted the 2013. I don't have that one. I had the 2014 and 15, and that video is available here. Yes, yes. Okay. Let me just make sure that I have this. Okay, so what we're going to do is we're going to do a final exam from 2011, 2012. And yeah. The only thing that all these exams are missing is the multiple choice. Again, the multiple choice will be based on terms, conditions, quick calculations that you should be able to do. So without further ado, we should start. I have... There we go. So this one says, express the following argument symbolically and use a truth table to determine if it's valid. Okay. So what we'll do, and this is kind of nice, this says, Steve will attend the matinee and or the evening show. So for number one, now the nice thing about your final exam is you'll be able to write on the page directly. And so what we'll do is we first have to define our propositions. So we'll say that Steve will attend the matinee, so we'll let M be, Steve will attend the matinee. And the next one that we have is E, be that Steve will attend the evening show. Okay. And I think that's all that I need to write out for that. So writing this symbolically, I have Steve will attend the matinee, so I have first thing is M. Then the next one is and or, so that's, we use the disjunction. We have E. And so that's our first premise. The second premise is that Steve does not attend the matinee, which means that it's not M. So therefore, Steve will attend the evening show. And we said that it was E, so there we go. So I have premise, premise, conclusion. Now I need to show that this is valid. I need to determine if it's valid. So what I'll do is I'll write it out here. I have M, I have E. These are my two prime propositions. And the next thing that I have is I'll have M or E. I have not M. And I'm also just going to rewrite E over here. So, just filling in the truth table, I have 2 prime propositions, which means that I'm going to have 4 lines, 2 to the 2. This disjunction means that it's got to be either one or both of them have to be true for it to be true. So I have 2 true, so that's true, 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 and here's a false. With the negation, we just flip from true to false and from false to true. And I'll just copy out E. Okay. Now this is the premise here. I also have the prem here. And here's my conclusion. So for an argument to be valid, the premises have to be true. When the premises are true, then the conclusion must be true. So we go through here, and this is the only line right here where I have 2 true premises and the conclusion is true. So since the conclusion is true, whenever the premises are true, the argument is valid. Okay. Now we're going to move on to the next question. This is part B. Use the laws of logic to determine if the following argument is valid. Okay. Now I can already tell you it is valid, and the reason being that if I assume that the premises are true, so that means that P or Q is true, and this has to be true as well, which means that since I don't have P, I have to have Q, and that's my conclusion. So quickly I can check that this is a valid argument. So, and then there's a little hint. It says, show that this is a tautology. And so they kind of gave it away, saying that this is a valid argument. So we'll do that. But basically, it's you take your premise and any other premise, you have another premise, and that implies the conclusion. For this to be a valid argument, it has to be logically equivalent to a tautology. Okay. So I have to show this. So here's my proof. I have P and Q and not P, which implies implies Q. Okay, so in the next step, what I'm going to do is I'm going to apply the implication rule so that I can get rid of this arrow right here. So doing that means, so when we had the implication rule, we had P implies Q is logically equivalent to not P or Q. So in this case, I'm treating this thing as my entire P. So I have to do the negation of it, so all that, or Q. So just rewriting this in. Okay. Now you don't have to actually justify each step in here. This is the implication rule. Okay, so the next thing that we have, well, I'm going to shove the negation inside of the brackets. So now when I distribute the negative, like using De Morgan's rule, the negative is applied to the first argument, or the first premise here. And there I have the negation being applied to the and here, which switches to becoming an or. And then I have two negatives for the P. So this is De Morgan. Okay. Okay, now I have two negatives, so that simplifies down to just P. So that's using my double negative rule. Okay. Then the next thing I have is I'm going to shift the brackets, and I can do this by commutativity. So by commutativity, I'm going to do this. Or, okay. So this is that's the associativity, because that's just shifting the brackets. Commutativity is when I change the orders. So, and I'm not doing that. I'm just moving the brackets. And I'm almost done, because I can treat that just like a single proposition. So this is like R, and I have this over here is R. So what I really have is not R or R, and we know that is the excluded middle rule. So that is logically equivalent to a tautology, and that's by the excluded middle. That's it. So I proved it. I showed that the argument, that the two premises implying the conclusion is logically equivalent to a tautology, which means then that it's a valid argument. And somebody was asking last night about doing counting questions. So I made sure that this one had some counting questions that we can do. So this one is number 2. Here's A. So I have, at a book fair, 3 calculus books. Okay, so I'm just going to start to write down information that I'm given. So I know that I have 3 calculus books. I have 4 algebra. And I have 2 geometry. Okay. And they're displayed on a shelf. So we're going to put them on a shelf. So they got to all line up. So I got to have, you know, how many ways can I have 3 calculus, I have 4 algebra, and I also have 2 geometry. Okay, now these are all supposed to be different books, I assume. So with this, if assuming that they're all distinct, this one says the 9 books can be arranged on the shelf. Yeah, and there are 9 because I have 7 plus 2 gives me 9, so there's 9 in total. So for part A, the number of ways to line them up on the shelf. So I have 9 choices for the first book. I have 8 choices because I have 1 removed. So all the way from, so I have 9 choices for the first book. I have 8 choices for the second book. I have 7 choices for the third book. 6, all the way down to the last book. So, you know, that's a lot of writing. We were just simply looking for, in this case, realizing that it's just going to be from 9 all the way down to 1, it's just simply 9 factorial. Now that's quite large. We don't expect you to calculate something that big. But there were 3 marks for it, so. The 9 books were arranged on the shelf so we'll move on to part B. The 9 books were arranged on the shelf if the books on the same topic were placed together. So something like this, right? But here's the problem that we have. The first thing that we need to do is we'll have to group them all together. So we have 3 topics. So how many ways can I permute these topics? Well, there's going to be, I have 3 choices for the first topic, I have 2 choices for the second topic, and then 1 choice for the next topic. So by the topic, I'll have 3 choices for the first one, I have 2 choices for the second topic, and 1 choice left over for the one topic there. So this is for the topics. Then for the next one, they can be, you can change the order. So inside of this, I have 3 of them, so that will be 3 times 2 times 1. So for the calculus books, I have 3 factorial. There's 3 factorial ways I can permute them. Inside of the algebra, I'll have 4 factorial. And then lastly, I'll have 2 factorial for the geometry books. So again, I'll have 3 factorial times 3 factorial times 4 factorial times 2. Okay. 3 times 2 is 6, so I have 6 here as well. Now I have 4 times 6 gives me 24, and then I have just times 2. And that's it. I have a good question. On the exam, will it be stated that we won't have to calculate large factorials because people will spend time calculating that? On the exam, we'll specifically tell you, leave it in a notation that we can understand. Otherwise, there'll be some things that we'll expect you to calculate. 9 factorial is a little large. We would expect you to be able to calculate, say, 5 factorial, that's 120, or maybe 6 factorial, which is 720. Smaller ones. 9 factorial is a little high. So I hope that answered your question. What else do I have next? So for part C, this one says you select 2 books which cannot be on the which cannot be on the same topic. Okay, so I have 3 calculus, 4 algebra, 2 geometry. Cannot be on the same. So a quick way I can, the way that I can see this is to do this using, let's use an indirect method. Because I'm picking 2 books, I don't really have to care about the order. It doesn't really say the order. It says I'm selecting 2 books. It's not like I'm lining it up on a shelf. So what I'm going to be using is not permutations like I did in A and B, but I'm picking the 2. I'm going to be using combinations. So I'm going to use an indirect method. And the total number of ways that I can pick 2 books from 9, well, it's a combination, so we'll use 9, choose 2. Okay, so this is the total number of ways to pick 2 books. Now this is going to include the possibility that you're going to pick, 2 of these same calculus, or 2 calculus books, and we don't want to do that. So what we need to do is also remove the possibilities where we are picking 2 calculus books, or 2 algebra books, or 2 geometry books. So that's where we have those cases, right? We're removing those cases we don't want. And in this case, I have 3 calculus books I don't want. So there's 3, from the 3 calculus books, I'm going to pick 2 of them. And that's something I don't want, so I'm removing that. The other possibilities, because I have the OR here, this is the sum principle. The next one I have is I have 4 algebra books. So from those 4 algebra books, I don't want to pick out 2 of them. And lastly, I have the 2, and I don't want to pick there. Okay. So let me just move that back up. These are fairly straightforward to calculate. And these are fairly simple numbers. Immediately also, so this is the case where I'm picking all calculus books. So those are 2 CCs. This is where I've picked 2 algebra books. And this is where I've picked 2 geometry books. Okay. So a quick way to do this would be using my Pascal's triangle. Okay, so for this 9 choose 2, I'm going to have to actually do a little bit of a calculation, but that just is 9 factorial over 2 factorial. 9 minus 2 gives me 7 factorial minus. And so now I need to do 3 choose 2. So I go to my 3rd row here, and I need to choose 2. So that's 0, 1, 2. So there's 3. Plus, I need to do 4. So I go to the 4th row, and I need to pick not 0, 1, 2. So there's my 6 right here. So there's 6. And lastly, how many ways can I pick 2 objects? How many ways can I pick all 2 objects? Well, there's only one way. So again, if I was to go look this up on the table right here, there's this is the row for this. So 0, 1, 2, and there's only one way to do that. For people who've never seen Pascal's triangle, remember there was a formula that we had previously that showed where we could, that the numbers for the next row were just adding up the previous ones, right? So if you wanted to construct it, it's just 1, and then the next row is 1, and then 2, 1, and then this one, I have 1 plus 2 gives me 3, 2 plus 1 gives me 3. Right here I have 1 plus 3 gives me 4, so on and so forth. Wouldn't it be much simpler to use the basic combination formula? If you wanted to, yep. Wouldn't it be much simpler? There's, if you enjoy doing it that way, go ahead. Use a way that you're very comfortable with. So I have 3 plus 6 gives me 9 plus 1, so that'll give me 10. I sure hope that's right, right? Good. So I have the 2 goes in the 8 4 times, so I'm left with 9 times 4, which is 36 minus 10, and that equals 26. Somebody was asking the formula. The basic formula should be, I'll write this in purple. So the other class was using this notation, the C n comma r, but the other way of writing it is n choose r, and that's n factorial over r factorial n minus r factorial. Okay. Some people, so this is the formula right here. It's not, somebody has written in chat n factorial over r factorial n minus 2 factorial. No, it's n minus r. So just be very careful, right? And she's asking 3 plus 6 plus 1. Yes. So in this case, I'm doing an indirect method. So I have the total number of ways of choosing 2 books. So the total number of ways is, from those 9 books, I'm going to pick 2 of them. So this is 9 choose 2. Minus, I have the cases that I don't want, right? Because they can't be on the same topic. So this includes all the ways, so that also will include the ways in which I'm picking 2 books that are on the same topic. So I'm going to remove these. So I do minus, and these are all the cases where I have 2 books that are the same topic. In this case, I have 2 calculus books, and this is not what I want. There's 3 choose 2 ways of doing that. Or I have the case where I have 4 algebra books, and I'm going to remove, so this is 2 algebra books. So there's 4 algebra books. I'm going to choose 2 of them. And so there's 4 choose 2 ways to do that. And then I also have one more case where I have 2 books that are geometry. And from those, I'm going to pick 2 of them. So this is the last case. So there's 3 cases that I don't want in this total number of ways. So for that, the number of ways that I could have picked 2 of those calculus books was 3. The number of ways of me picking 2 algebra books was 6. And the number of ways that I could have picked the 2 geometry books was 1 way. And these are not what I want. So in total, there was 3 plus 6 plus 1. There was 10 ways that I didn't want to have included in the total number of ways. So I removed that from the total number of ways, and there was 10 ways I didn't want, because there's a total of 10 ways in which I would have the same topic, and I don't want that in that. So I'm left with just 26 ways in which I can pick 2 books not on the same topic. Does that help? Okay. So the next one I have, next question, more counting, because people wanted counting. Yeah, I do not know where the triangle came from. Okay. Just a quick detour. No, not the Bermuda Triangle. It's called Pascal's triangle. And Pascal's triangle kind of starts out like this. So I have 0, choose 0. I have 1, choose 0. Okay, so I have this. Now, Pascal's triangle works because it relies on Pascal's theorem. And I think in Dr. Brimberg's class he showed you this formula. And now he was proving it algebraically, but something along, you know, like this. Okay. It works for, well, yeah, it'll work, well, not just for really small values, but, you know, it would take much more time as you get more and more values, right? So, you know, for very small values, it's quick for me to just kind of write out a couple of lines of Pascal's triangle. But remember, this is what Dr. Brimberg probably proved to you. Probably he writing it in, you know, this notation, C n r plus 1 equals C n plus 1 r plus 1. But basically, all it was saying is it takes two of them. They have to be the same number, so here it is. And then I add them together, and that would get me to the next row here. So all it was doing is Pascal's triangle is a plus, and it gives me the value for the next one below it. Okay? And it works for here as well. You know, whatever. So I have, it can go up as high as you want, not just 4. Exactly. I can keep going. I'm just running out of room on my page. But I have 0, choose 0. So I have from 0 things, I'm going to pick 0 things. So there's only one way to do that. I have one thing here, and I'm going to pick none of them. There's only one way to do that. I have one thing. I'm going to pick that one thing, so that means that's 1. And now this is where I start to use, so I have 2, choose 0. Again, I have 2 things. I'm not going to pick any of them. There's only one way to do that. And now I can start to use Pascal's triangle, which is I can add these 2 ones, and I get the value for the one below. So I have 1 plus 1 gives me 2. And then I have, again, 2 things, choose 2. Again, that's 1. And so for this row, oh, it's going to get a little cramped. Sorry that I didn't do that properly, but now I do the same thing. 1 plus 2 is 3. 2 plus 1 is 3. And I have 1 there as well. And I also have 4. So I have 1. This one is 1 plus 2 gives me 4. 3 plus 3 gives me 6, and I have 1 plus 3 gives me 4, and then the last one is this. So these each correspond to these values. So I have 4 choose 0 is 1, 4 choose 1 is 4, 4 choose 2 is 6, 4 choose 3 is 4, 4 choose 4 is 1. And that's just kind of Pascal's triangle. So it's just a quick way for me to do something. You know, if it gets into things like, you know, 12 choose 3, you know, that would require me to do 12 rows. At that point, I would look to see if there are other ones that I needed to calculate. If not, I would just calculate it using the regular old formula, which was n choose r, which is equal to n factorial over r factorial n minus r factorial. Is that helpful? which is kind of nice to see if moving on to the next one, which is there we go. So I have part A. So a student takes an exam and is required to answer exactly 7 out of 10 questions. In how many ways can 7 questions be selected? A, if there's no further restrictions. And, okay. I have a question. What's the percentage of the exam is multiple choice? I think, let me see. About 16% of the exam is multiple choice. A student, okay, so we have 10 questions in total that I have, and I need to pick 7 of them. So that's just simply using our combinations because I don't really care about the order I'm going to answer them. So I have 10 of them, and I'm going to pick 7 of them. So in that, I'll start to use my formula again. So that's n choose r, which is n factorial over r factorial, n minus r. This is something that you would be expected to calculate. It's fairly straightforward, and you get 4 marks. So, you know, we expect, well, usually roughly a mark a minute. We'd expect you to spend like 4 minutes on this, so yeah, calculate this. So 10 factorial. That's a little top tip. If, you know, the mark is like 1 or 2, don't spend as much time as, say, something that's worth 4 marks. 10 minus 7 is 3. And I expand this out again, so I got 10 times 9 times 8 times 7 factorial all over 7 factorial. And then I'm just going to also write out 3 times 2 times 1. So the 7's cancel, so I'm just left with 10 times 9 times 8. Some quick simplification. 3 goes into 9 3 times. 2 goes into 8 4 times. So in the end, I'm left with 10 times 3 times 4. So I got 10 times 12. And so it's just 12 with a 0 on the end of it. So there's 120 ways to pick 10 questions. From the 10 questions, pick 7 questions. So that one is done. B. If exactly 2 of the first 3 questions must be answered. Okay. How would we account for the 10 by using How do we account for the 10 by using the n factorial over r factorial? Well, remember, when we're looking at this, I have n choose r. This tells you that it's the total number of the objects. So in this case, there's 10 questions. And here I have r. So this is what the number I want to pick. The number of objects I want to pick. So when I say that, there's 10 questions, there's 10 total objects. And here, this is the 7. This is telling me the number of objects I want to pick. So I have 10 questions in total, and I'm going to choose 7 of those. Does that help, Owen? Just ask. Okay. Okay, so continuing on then with the 3B, if exactly 2 of the 3 questions must be answered, so 2 of the first 3 questions. So this is going to rely on the multiplication principle. And remember, with the multiplication principle, it's, you know, I have a certain number of options in the first part, and then I do something else. So when I do that, let's see. So I do something like using the multiplication principle. We were kind of using these boxes. Because what it says is, I'm going to do this first. I'm going to pick 2 of 3 questions. So 2 of the first 3 questions. Now, how many ways can I do that? Well, there's 3. Choose 2 ways to do that. And then, with the multiplication principle, and then I'm going to pick questions for the remaining. So I have to, you know, in total I have to have, I have to pick 7 questions in total. So what does this mean for the next part? So I picked 2 questions already, and then I'm going to have how many questions remaining that I can choose from. So let me write this out. Okay. Question 1, question 2, question 3, question 4. So I have these 10 questions, and what it's saying is I need to answer exactly 2 of the first 3 questions, which means that from these, I need to pick 2 of them. So pick 2. And so the number of ways to do that is 3, choose 2. So that's what I have here. And then I have to pick from these. So how many do I have left to pick? I have 1, 2, 3, 4, 5, 6, 7 questions in total. And from those, I still have 7 questions in total that I need to pick. So I picked 2 already, and let's say I picked 2. Then I need to pick another one, say 3, 4, 5, 6, 7. So in the number of choices I need to make is 1, 2, 3, 4, 5. Now, I don't have to pick those ones exactly, and it's just an example, but I have 7, choose 5, because I have 7 remaining questions and I have to pick 5 of them. So the reason why I love this notation in particular is because this multiplication has broken up this. So when you look at this, I have 3 plus 7. So 3 plus 7. There was 10 things that I had in total. And quickly, just me checking here, I have here 2 plus 5, which is 7, which is kind of very similar to what I had originally up here. So I've just broken up this 10, choose 7. It's just me doing something a little different. So there's no restrictions on this one. Then in this part, I'm actually kind of having a decision in here. So I picked 2 of the first 3 questions, and then I pick 5 of those from the 7 remaining questions. So I should calculate that. So let me write this out in good. I have 3, choose 2, times 7, choose 5. I think he was saying, how do we account for the 10 by using... remember, that was... Somebody was asking just about an old question, and that 10 in there was... Those were the number of cases that we wanted to remove from the total number of ways. So that's where that 10 came from. It's not accounted for in that formula. That came from me doing the total number of ways and then removing the cases I didn't want. So I have 3 choose 2 times 7 choose 5. So I have 3 factorial over 2 factorial. 3 minus 2 gives me 1 times 7 factorial over 5 factorial. 7 minus 5 gives me 2 factorial. 3 times 2 factorial. The 1 is just 1 factorial. Somebody is asking, what is the format of the exam? Like, how many multiple choice and long answers? There's, I don't think that was released, but I can tell you approximately 16% of the exam is multiple choice, and then the remaining would be long answer. I just can't tell you exactly how many questions there are. So, just carrying through the calculation. Again, there is 4 marks for this. And I'm going to cancel this 2 into the 6 so that I'm left with 3. 6 divided by 2 is 3, so that's good. So that I'm left with 3 times 7 times 3. 3 times 3 is 9 times 7 gives me 63. Okay, everyone okay with question 3? This is question 3. Okay. As Owen said, how would we account for the 10 by using? Somebody's asking about question 2b. In question 2, so there was question 2 that I had. So I don't think it was part A that you were questioning. I don't think you're questioning part B. Second. Just asking the question if she means in 2C. Now, this is the question. Do you mean this 10 right here? I have to just wait. Do you mean this one right here, this 10? Okay. Okay, so we just go back to that question. So in 2C, it says you have to pick two of the books which cannot be the same topic. Okay. Now this says that you can't have it in the same row. So, well, you're just picking these books. You've got two books, and it says that it can't be the same topic. Okay, so it means that, you know, picking two calculus books, we don't want that. But how many ways can we do that? Well, there was 3 calculus books, and we're going to pick 2 of them. So that's the number of ways to do that. We don't want to include also picking 2 algebra books. We don't want that. And the number of ways that we could do that was we had 4, there's 4 algebra books, and we're going to pick 2 of them. So that's the number of ways to do that. And we also don't want to pick 2 geometry books. And so there was choose 2 ways to do that. So these are all the ways, in which these are the same topic. So we don't want that. These are not good. Now, these are cases, and by the sum principle, we just add them up. Okay. Now, these are the number of total ways to do the same topic. And yes, I think you use the formula for each of the cases that you don't want, so that you would have to use the formula 4 times. Yes, that's correct. So what I have here is, so these are the same topic, and the total number of ways is 9 choose 2. So this is all the possible ways of picking it. And so this is all ways of picking the book, picking 2 books. And so that includes picking 2 books that would have the same topic. And that's not what we want. So what we do is we just remove them with a minus. So that returns us back to what we originally said. This was the total number of ways, which was 9 choose 2. And we're going to remove, so there's the minus, we're going to remove all the cases where we're picking 2 calculus books, 3 choose 2, or the cases where I pick 2 algebra books, or, oh, I see. Oh, okay. The way that I was, okay, yes. The way that I was doing this before was I had just done this using the Pascal's triangle. Instead of me working out the formula for 4 times, I just worked it out for this one. And because this was fairly straightforward, what I did was just looked at my triangle here. So in this case, it was the 3 choose 2. So this was my 3rd line, 0, 1, 2. So that gave me my 3 right here. Then I had 4 choose 2. So I had the 4th line, choose 2, 0, 1, 2. So that gave me my 6. And then I had 2 choose 2, and that's just 1. So that's how I did it there. So that's how I was calculating those, as opposed to me using the actual formula. question 4. So of the 130 students who took the exam, so this is important right here. This is a question in the question here. 130 students who took the math exam, 90 answered the first question correctly. We have 62 that answered the second question correctly, and 50 that answered both questions correctly. So that means that I'm going to have a universal set. The universal set is 130. I'm going to define my sets. I'm going to say that A is students who answered question 1 correctly. B is the students who answered question 2 correctly, and that's it, because the 50 is both of them. So just writing out my given information, I have A is 90, the number of elements that are in set B is 62, and the number that are in the intersection is 50. Okay. So, me being a visual kind of learner, I start to write out a Venn diagram. So, plugging this in, I know that I have 50 here. And then from the 90, I'm going to remove the 50 so that I know that I have in here 40. So the 40 plus 50 gives me the 90. That's good. The next one I have is 62. So the 62 minus the 50 gives me 12. And now the last thing that I have to do is I know that there's 130 in the total set, the total universal set, and from that I'm going to subtract the 40. I need to subtract the 50, and then I also need to subtract the 12, so that leaves me with 28. So the total that I have then, so that should add up, so 28 plus 12 plus 50 plus 40 gives me 130. And yeah, that seems to be right. So 130, good. So I've done my Venn diagram. So these questions are kind of straightforward. And let's see, part A. How many students correctly answered the first or second question or both? Okay. So what it's asking for is how many students answered the first question or the second question or both. So we are thinking immediately union. We got the little U for union. So see? So we'll use the union. So that's A union B. So that is the students who answered question 1 correctly or answered question 2 correctly or both. So reading off this, I could just say it's 40 plus 50 plus 12 because it's just everything in A. So it's just everything. I don't want to start shading it, but it's just everything in there, not including that. So I have 40 plus 50, so that is 90 plus 12, which gives me 102. Okay, so that's using the Venn diagram. Some people might not like using the Venn diagram, so they want formulas. Okay. So the other way that I could do this is using the principle of inclusion-exclusion. So without, let's pretend that never happened. So using our formula, we can use the principle of inclusion-exclusion, which is we have the number of elements in A plus the number of elements in B minus the number of elements in A and the intersection, right? Because what ends up happening, so I have A, I want all the elements in A, I want all the elements in B, but that means I've overcounted this twice. I've done A, here's B, and so in here I've double counted in that, so I need to remove that. So that's what that does. That's the principle of inclusion-exclusion. So substituting in my values here, the number of elements in A is 90. The number of elements in B is 62 minus the number of elements in 50. And I mean, I could, 90 plus 62. So there's the 2. 9 plus 5 is 115, and then plus the 50. So that gives me 2. Oh, yeah. No. 152 minus the 50. So that gives me 102. Okay, so that's part A done. The next one that I have is how many students did not answer either of the two questions correctly. Okay. So for part B, what it's asking for is the complement of this. What is, here's it says does not answer either questions correctly. So what that says is A union B. So that's all the students who answered question 1 right, or answered question 2 right, or both. And what we want is the complement. We want everything outside of that. Now, just using our Venn diagram, we know that this is the union of A and B. So the number of students who did not answer either of the two questions correctly is not in here. It's just right in here, which I wrote was 28. So it's 28. Okay, so that was using the Venn diagram. Now, alternatively, for people who like using formulas, we can do this. Okay, so what this is saying is that I don't want to have A union B. So it's the total number of elements. So it's the total number in the entire universal set, so everything in here, minus the union of it. So this is our complement rule. Now, we knew that there was 130 students that we had, minus, and we calculated A union B in the part A, so I can just write 102 here. And so that gives me the same answer, 28. Okay, part C. This one says, Part C, how many students answered either the first question or the second question correctly, but not both? So, I'm running out of room, so what I'll do there. So for C. So the number of students that answered either that, but not both. Well, reading that off of the Venn diagram, that is 40 plus 12. So it's all of the students in here who answered A correctly. This is all the students in here that answered B correctly. And we didn't want where both of them answered correctly. So in that case, what I got was 52. Now, using a formula, what does that want? What we want is basically, I should just kind of quickly draw in the set that I want. I want this set in here, and I want this in here. Okay. So what that is it's the number of elements in, so just for us, we're going to write this out. It's A intersect B complement. So that gives me everything outside of B that intersects with A. So that gives me this region right here. That gives me this one right here. Then the union of that, and then what I want is this section right here, which is everything outside of A, everything outside of A that intersects with B. That's this area right here. And notice that these are two disjoint sets, which means that, okay, so since they're mutually exclusive, I don't have to worry about the intersection, right? Plus A intersect B. There we go. If we just refer to the Venn diagram for the answers, is that sufficient? Okay, so somebody asked me, is it okay if we just refer to the Venn diagram for the answers? Is that sufficient? And my answer is yes and no, because what I want to see something like this, where I see, you know, you're telling me A union B, so the number of the elements in there is equal to 102. So yes, you can tell me in there, but you should tell me what set that you're actually looking at. Right, so for part A, that was that students got question A or B or both correct. This one is saying that this is that the students, these are the set of students that did not get A or B or both correct. So just writing this out helps. If you make a mistake using your Venn diagram, it helps me to figure out what you were doing, what thought process. By writing down just a couple of numbers and you make a mistake, these are points that you might not get, because if it's incorrect, it's just wrong. So again, we have, you know, there's 10 points here. Tell me a little bit about what you're doing tell me what set that you're using. Okay. So in that, to do this, just using this. So again, it was for this area. It ends up being 40, but what we'll do is we have the A minus the complement of it, which is 50, plus, then I have a complement, which gives me 62, minus the 50. So again, here is my 40 plus 12. So again, these are the numbers that are corresponding to here, and that's what I wanted right here. And so that gives me 52. So that's how I read it off of the Venn diagram, and I also could use it using some formulas here. Okay. And the last one is how many students missed the second question? Okay, so what it's asking for is how many students missed the second question. Well, really what it's asking is, this is the ones that got all the second question. So what it's asking for is, what is this right here? What is this? We want that area. And what is that equal to? Well, okay, let's see, D. So let me just pull back that question. How many students missed the second question? That is everything outside of B. So that means that it's B complement. So to get the complement of B, it's the universal set, the number of elements in the universal set. Oh, okay, before I do that, how would I read this off the Venn diagram? Well, it's everything that's shaded. So it needs to be 40 plus 28. So that'll give me 68. Okay, so to use a formula, I'm going to use the complement rule. So it's the total number, it's 130 minus B, which is 62, which still gives me 68. And that's the end of question 4. Question 4 is done. Here's another one. This is, okay. So this is a little bit of logic now. In question 5, it says if A and B are independent sets, they must also be mutually exclusive. So So this is saying if A and B are independent, then A and B are mutually exclusive. So this is an implication. So we assume that this is, we want to see if this statement is true. So let me think about that. Okay. So this means that if A and B are independent, so we're given that A and B are independent, then we have a formula that we can use for that. So it means that the probability of A intersect B is simply just multiplying the two probabilities of A and B together. Okay. So if I just start to draw this, and here's my set, here's A. So I know some people are used to seeing circles, but here we go. There's some, this is the probability of A here. And here's the probability of B. We'll call this B. Here's the probability of B. So if I multiply the two probabilities together, it gives me the intersection. So okay. So, which means then that this probability is not 0. So then this means that okay, so it's not empty because we got an area in here. Which then means and remember when we're talking about mutually exclusive sets, so here's A and here's B, mutually exclusive sets, there's no overlap, so there's no intersection. So since the intersection is not empty, so it's not the empty set, then A and B are not mutually exclusive. So I would say, sure, this is possible. I think that there should be one more thing that we add in this. I think that is the answer that they were looking for 5 marks. But there should have been, I think, something added to it, which was assuming that the probability A is greater than 0 and the probability of B is greater than 0. because I know that these are probabilities that are greater than 0, which means then they have to have some area in here, which then means that I have to have an intersection, which then means that they can't be empty, which then means that it's not mutually exclusive. The problem is if I do set probability of A, this is something what we call a trivial example, but the probability of A is 0 and the probability of B is 0. Well, this is where it starts to fall apart, and we say that A and B are independent. Then that means that A and B is equal. So since they're independent, we can use that formula, probability of A times the probability of B. But since the probability of A is 0, and not necessarily, both of them have to be 0. Let's just say that one of them is 0. 0 times, say, probability. We don't even have to do it for that one. Times B, that'll give me 0. Which then means then that A intersect B has to also then be empty. Which then means that A and B are mutually exclusive. So I think there was just a little subtlety in that, but I think this is the answer that they were going for. But I think that you have to assume that the probability of A and B is greater than 0. Because if I don't, one of them could be 0, which then leads to, assuming that they're independent, one of these would be 0, which causes the probability of the intersection to be 0, which causes it to be an empty set for the intersection, which means that it is, in fact, mutually exclusive. Okay. Ooh, 6. Okay. So we have the probabilities. So I have probability of A is equal to 0.2. Probability of B is 0.6. And the probability of A intersect B is 0.1. So, question A, or part A. So I have the union. So what I want to do is, well, probably before I want to do anything, is probably draw my Venn diagram. And I'm working in a sample space now. Here's A. Here's B. And I'm told that this is 0.01. This is, for A, it's 0.2. So 0.2 minus 0.1 gives me 0.1 here. And lastly, I have 0.6 here. So 0.6 minus 0.1 gives me 0.5. And we know that everything in the sample space has to sum up to 1, right? So I have 0.1 plus 0.1 is 0.2. 0.2 plus 0.5 is 0.7, which means then that everything outside of this is 0.3. 0. Oops. There we go. Okay. So I guess I can look at this quickly, and I could, from a Venn diagram, say, oh, the probability of A union B, 0.1 plus 0.1 plus 0.5, that gives me 0.7. Now, alternatively, if you didn't have that, what would you do? You would use the addition rule, which is very similar to our principle of inclusion-exclusion. So it's everything in set A plus everything in set B, so or event B, and then we subtract the intersection because we're double counting. And we just substitute those values in. 0.2 plus 0.6, that's 0.8, minus 0.1 gives me 0.7. Good. B. Now the probability of A complement union B complement so that's everything outside of A. So maybe I should draw that in. I can draw a nice little Venn diagram for this. So it's everything outside of A. Everything outside of A. Okay. So everything outside of A. Oh, and then I need to have everything outside of B. So everything outside of B. So I've already colored that in. Everything outside of B. There. So it's everything in there but the intersection. So I know that everything but the intersection here. So everything here, so that's 1 minus the intersection is 0.1. So it's 1 minus 0.1 is 0.9. Okay. Equivalently, just using a formula, I have A complement union B complement. And I can rewrite this using De Morgan's law so that I have A intersect B complement. So that's equal to 1 minus P of A intersect B, which, surprise, surprise, is exactly how I solved it for the Venn diagram approach. Okay. For C, just a second. So for C, I have the probability of A complement intersect B complement. And what does that mean in terms of? Well, I'm going to use De Morgan's law. Which means that this is my De Morgan's law, which is A union B complement. So that means that it's everything outside of the union of A and B. So that's the union A and B, so it's everything outside of the union. And from our Venn diagram, we know that that's 0.3. So alternatively, using kind of our formulas, same idea, using the De Morgan's law, it's equal to 1 minus the intersection, which was 0.1 there. Uh-oh. I made a mistake. Did I make a mistake? Yes, I did. Because I wrote down... This is where I made the mistake. I made a mistake there. There we go. Union. 0.7. Perfect. Yes, thank you. Yeah, it would be bad if this was my intuition here and it didn't match the same as the answer here. So, good. Okay, I have D. Part D. It's good that people are watching. Probability of A intersect B complement. So what is that? In the Venn diagram, just reading off of it. So that's everything outside of A, or sorry, that's everything in A. Right, there's A. And everything outside of B. So B complement there. So everything outside of B. So here's everything outside of B. Gotta be careful. Everything outside of B. Okay. So this is the intersection. So I need to look at where it's crosshatched. And where it's crosshatched is right in here. This moon-shaped piece. So this is what I want. And in that case, reading off the Venn diagram, it's just 0.1. So how would I do this with the formula? That's the probability of A minus the probability of that intersection. Okay, which is 0.2 minus the intersection, which is 0.1, and I'm back to 0.1. Okay, and the last one is the probability of A union B complement. Okay. So the union means that I just keep coloring in. So I have A, so it's everything in A. And then also everything outside of B complement. So everything outside of B. Let's keep coloring it in. Everything outside of B. Which means that it's just that one piece that is missing. So I just looked that up. So it's everything in here is 1 minus, I'm going to subtract that moon piece right here, and that turns out to be 0.5. So I'll subtract that. So that should give me 0.5. Now, how could I do this using formulas? What I can do is I have the probability of, I can use my addition rule. Okay. So the probability of A is 0.2. And the complement of that, that's 0.4. And then minus, we already calculated that up here, so that's 0.1. So 0.2 plus 0.6 gives me, okay, so 0.2 plus 0.4 gives me 0.6, minus the 0.1 gives me 0.5. Okay, and so that's the end of question 6. Will there be questions that dictate how it must be solved? Yes. So, for example, using the laws of logic to prove a statement, if you had used truth tables on it, you would receive 0. So there's an example, yes. Will there be many questions that dictate how? There's a few, at least one I can tell you. So an example of that is using the laws of logic. Yes. But we're fairly open, at least I am, we're fairly open about how you're solving problems. And as long as you're telling me what you're doing and you're communicating your thought process, whether it's visually or in the form of an equation, you have to be able to tell it to me clearly. And if you're, because what happens is we'll have, if you give me an answer and there's no, there's nothing to show, there's no work showing me how you got that answer, you run the risk of us not giving you full marks for it because we don't know how you got it. And even worse is if you was incorrect, you could lose full marks for that whole question. So that's not what we want. We want you to tell us what you're thinking. Someone's asking, how hard is the exam? I would say it's similar to past exams. Okay, somebody was asking me about previously about like probability trees. So this is a typical probability tree question because there is probability tree right in the question. So it says an urn initially contains 4 black balls and 4 red balls. So I have an urn. Okay, so I gotta make sure I'm following along what it's doing. That's the other thing with this type of course, is just keeping track of the information of what you know and what you don't know. In this case, we have an urn, so I'll write down it. There's an urn. Inside of it, I have 4 black, and I also have 4 red. An experiment consists of randomly picking a ball from the urn, replacing that ball. Okay. Selecting one ball from the urn, so picking one of these, and replacing that ball. So I pick it. Okay, so So earn, pick one ball. Okay. Then it goes back, replace. Plus 2 additional ones of this. Plus 2. Okay, so place original plus 2 new ones of the same color. Okay. Okay, and then picking another ball. Okay, so I've kind of captured the information for this. This tells me draw a probability tree for this experiment. Specify the probabilities and what they represent on each branch of the tree. Okay, so probability tree. Part A. You want my probability tree? Okay, so I'll just draw this in. So I have an urn. So starting with my urn. Oh, and what I'll do is define my events. Let B be selecting a black ball, and R be selecting a red ball. Good. So I can select a black ball, or I can select a red ball. Then after that, I'm told I'm picking another ball again. So again, I have a black ball, and then I have a red ball, I have a black ball, I have a red ball. Because what I have here, so this is, you know, my first draw, and here's my second. Because I'm just following it. So from my urn, I pick one ball, so it's either black or red. And then I replace the original one, and then I put in 2 new colors, and then I pick another ball. So this part right here is just going to affect my probability of picking a red or a black ball in the second one. So the probability of me picking a black ball or a red ball. Okay, so the probability of me picking a black ball, there's 4 black balls. In total, there's 8. So it's going to be 4 8s for that, or 1/2, but I'm just going to write 4 8s. There we go. Okay, so if I pick a black ball, that means that I'm going to replace it back into the bin. So in total, I still have 8 balls plus 2 more of the same color. So that means that in total that are in the urn now has not 8 balls anymore, but 10. So it means that I'm going to have 10 balls in total. Okay, so I have 4 black balls. I pick a black ball in this case, and I'm going to put in 2 more of it of the same, which means that if I pick that one on the second time, there's 6 of them that I can pick from. Which then means that there's still those 4 original red balls that I started out with. Okay. The other thing that I have is the other case where I have red. I pick a red ball, okay, and what I'm going to do is I'm going to replace that red ball again, back into the urn, and that means that I'm going to have 10 balls because I'm going to replace the original red ball back in, and then I'm going to add 2 more reds. So that means that instead of having 8 balls, I'm going to put 2 more back in, and in this case, I'm not just going to have 4 reds, I'm going to have 6 reds now. And in this case, I'm not going to, I pick a red on that one. That means by the complement rule, this should be 4/10. So I've done my probability tree. And then the next question says, what is the probability that the first ball drawn is black, given that the second one drawn is red? Now, the way that I've done this, I just use the same letters for drawing 1 and drawing 2. So let's see, what I need to do is convert this to words. So I have the probability that, given that the first ball is black, so I'm going to just say first ball is black. There's my given, is given that the second ball is red. Okay, so I've copied that down. So that's what the question is asking. And I can use my probability, my conditional probability for this. So this is, so what I want is the conditional probability. So it's very similar. So E given F is equal to the probability of E and F happening over F. So just in words, I have the first ball is black and the second ball is red, all over the probability that the second ball is red. Okay. Okay. Backstretch. Okay. Now, in my class, what we learned was right here. This is right here. I have the probability of B and B. So that is 4/8 times 6/10. I have the probability here. This is where I have B and R. 4/8 times 4/10. Here, this is the probability of being R and B. And that is 4/8 times 4/10. P. And I have R and R, which gives me 4/8 times 6/10. And what this is saying is what I did was in my class, I said, okay, here are my branches, and I'm going to name them. Here's 1, here's 2, here's 3, and here's 4. So I have 4 branches. And in this, what does this correspond to? The first ball is black, and the second ball is red. So that is B intersect R. So that's this one here. The first ball is black, and the second ball is red. So in this case, it's going to be branch 2. Okay. Now, the next part is I look in the cases where the second ball is red. I don't care necessarily what happened in the first ball. I just only care about that the second ball is red. So I go through my tree and I see black and black. Nah, don't really care about that one. I see black and red. This I do care about because this is the second ball. The second ball is red. So I care about branch 2. Or instead of that happening, I could have looked at, could I have red and black? No, I don't care because, again, the second ball is supposed to be red. So it's this branch right here, red and red. So this is where the second ball is red. This is the case. So I want branch 4. So that's all I need. So I need branch 2 over the branch 2 plus branch 4. So I have 4/8 times 4/10 over. And I need branch 2 again. So again, it's branch 2 all over again times 4/10 plus 4. So in this case, it's 4/8 times 6/10. Okay. Now, this is quick math to do now because I have 4 times 4 is 16 over 80. I have 4 times 4 is 16 over 80 plus 6 times 4 is 24 over 80. So that gives me 16 over 80 over, and then 16. Well, what I'll do is I'll just write 16 plus 24 over 80. Okay, and all I have to do is invert and multiply, so I get 80 over 16 plus 24. These 80s cancel, so I'm just left with 16 over 16 plus 24. So 16 plus 24 is 40. 16 over 40. And 16, oh yeah. There we go. So the way that I got that, just if you want to reverse that, I'm just dividing everything by 4. So 10 times 4 gives me 40. 4 times 4 gives me 16. So that's the probability of the first ball is black, given that the second ball is red. Oops. Okay, so I'm just checking to make sure if there's any questions about question 7. Yes. Well, so Ken was asking, is it all right if I reduced everything from the start? I ended up with 2/5. Yes. Yes. And if I wanted to write this in lowest terms, I should put 2/5. And how do I know if something is reduced to simplest terms? Well, the 5 is a prime number. I can't reduce it anymore, so that's good. But yes, 2/5 is good. Okay. Okay, this is question 8. I have the probability that a newborn baby will live 50 years or more is 0.8, and the probability that he or she will live 90 years or more is 0.2. What is the probability that a 50-year-old will live to be 90 or more? Okay, so again, okay, so again, I'll start to define some events. So let E be life is 50 years, 50 more or years, and that probability we're told is 0.8. And the probability that he or she will live to 90 or more is 0.2. So F, be that the life is 90 or more. So that's the probability of F is 0.2. What is the probability that a 50-year-old will live to be 90 or more? So what they're asking is what the probability of a 50-year-old, so given that they're 50, no, so we got to be very careful about this. It says, what is the probability that a 50-year-old will live to be 90 or more? So what we have to do is assume that the person is 50. Is 50 or more. So that's something that's given. We're told that. So that means that it's a given. So instead of what I was writing originally, it should be E is right here. So we're told that. And what we're asked is, what's the probability that they're going to be 90 or more? So using our conditional probability, I have the probability of F given E over the probability of E. Now this is saying, what is the probability that F and E? They're being very sneaky here, because most people are thinking, oh, you know, I'm given two events and here they are overlapping. Oh, this is what people are thinking. See, this is the guy, he's thinking on the exam. But really what's happened is the way that they've described it. We have 50 or more years or 90 or more years. And so the F is contained in E. Right? Because when we really look at that, we have 90 years, right? So they're going to live to be 90 or more. And that's going to be a smaller subset than the people that are going to live, that are living at 50. So these are 50 or more years, and inside of that, these are the people that are going to be 90 or more. So what does that mean? Well, what we want is that intersection. So we want that intersection. Well, what's the intersection? So it's everything that's in E that is also in F. So it's just this one right in here. So it ends up being that it simplifies down to just being the probability of F over the probability of E. Which then means that I go back up here. What's the probability of F? I wrote that down to be 0.2. Then I wrote the probability of E is 0.8. So I have 2/8 or 1/4. So that was 8. There's 5 marks right there. But there was a trick in that, and that was realizing that E, that event E contains F. So that F is a subset of E. So that was the trick. And that's how I was able to figure out what the intersection was. Okay, so there's the kind of standard question that we usually see, 9. Consider the following table of data for a random variable x. So I'm told this. So what is A supposed to be? So we have to remember that the sum of the probabilities in a probability distribution have to sum up to give me 1. which means that it should be 0.1 plus 0.2 plus 0.3 plus a equals 1. 0.1 plus 0.2 plus 0.3. So I have, here's 0.3 plus 0.3 gives me 0.6. And then I have the a, I bring the 0.6 over to the right-hand side. Gives me 0.3. Okay, B. Give the formula for the expected value of x, or mean value, and compute it. Okay, so the expected value is the sum of all x. So it's the value of x times the probability. So, you know, this is kind of slow way of writing it. So let me just do it this way. I have 0.3. So I'm going to multiply these together. So 1 times 0.1 is 0.1. 2 times 0.2 is 0.4. 0.3 times 3 is 0.9. And 0.3 times 4 is 1.2. I hope so. Good. And then I just add them up. Did I copy that wrong? Oh, it should be 0.4. Thank you, thank you, thank you. Yes, 0.4. So that should be 0.6. Thank you. Okay, then we just sum those up. What? Okay, somebody's saying no. What am I doing? Okay. So I have 0.1 plus 0.4 plus 0.9 plus 0.16. So there's 0.5. So 5 plus 9. 5 plus 9 is 14. 14 plus 16 gives me 30. So that's just 3. Okay, good. So after all of that, I mean, I could write this all out, but I'm just... That was what we're trying to do, is that. So again, you could write this all out. 1 times 2 times 0.2. So I'm going to... And that equals 3.0. Okay, so now we need to do the variance. The variance is equal to, and there's 2 different ways of doing it. I prefer doing it this way. Okay, so I'm going to calculate the variance of that. And the expected value, I'll just write down here. So here we go, E, expected value of x squared. It's the summation of all the x values such that I have x squared times the probability of x. So, you know, it's basically what we wrote up there, except each of these are going to have squares. So I have 1 squared times 0.1 plus 2 squared gives me 0.2 plus 3 squared gives me 0.3 plus 4 squared gives me 0.4. So 1 squared 0.1 gives me 0.1 plus I have 4 times 0.2. Yeah, 4 times 0.2 gives me 0.8 plus 9 times 9. 9 times 0.3 gives me 2.7. Good. I have 16. 16 times 0.4 gives me 6.4. Okay, and then we add them up. 6.4, so I have the I have 0.9, and let's go 0.9, 2.7. Then I have the next one, which is 6.4, 0, carry them 1, so 4, 10. I'm going to make sure that I'm not making a mistake when I'm carrying this through. So I have 10 minus, and then my expected value I've already calculated up here, which is 3, so it's 3 squared, which gives me 10 minus 9, which gives me 1. And the last one I was asked to do was give the formula for the standard deviation and compute it. Okay, and the standard deviation. So there's two ways of writing the variance. The other way of writing it is sigma squared. The standard deviation is just sigma, which is the square root of sigma squared. So all you have to do is just taking the square root of the variance. In this case, the square root of 1. And we all know that 1 squared gives us 1, so square root of 1 is 1. So we're done that question. Okay, so just checking Q9. Okay. So Q9 looks good. Okay. Why did you minus 9 in... Oh. Okay. So the question was why did I minus a 9? And this is my formula for the variance. I have the expectation of x squared minus the expected value all squared. So what I did was I calculated the expected value of x, which ended up being 10, and then I subtract 3 squared, which this was the expected value that we calculated in part B, so there is 3. So that is the expected value of x. 10 minus 3 squared is 9, minus, so that equals 1. Okay. Good. Okay. So moving on to the next one. So the Army is investigating the quality of a large lot of old ammunition. The defective rate, of the rounds in this lot is thought to be about 10%. The probability that a randomly selected round will misfire is 0.1. Okay. A random sample of 3 is selected. So in that paragraph, we have to define a couple of things. Oh, and it tells you X. So X is the number, is the random variable of the number of rounds that misfire. Okay. Now it's going to say explain why X follows a binomial distribution. So we're going to be told that this is following a binomial distribution. So this is X, and here's follows. And then we have the B. So this B is the binomial. So it follows a binomial distribution. And in this binomial distribution, there are 2 parameters. So in this case, those 2 parameters that describe a binomial distribution that we need is N and P. In this case, we're told that N is a random sample of 3 rounds. So that's the total number of rounds that they're testing. So it's 3 here. And we also are told that P, well, we'll let P is the probability of success. And what it's saying is that it's the number of rounds that misfire. So we want a success is going to be a misfire. So it's the probability of success. And I put those in little quotes because really what we want is the misfire probability. Okay, so that's 0.1 because we're told that. Good. So this is just, before we start, just trying to figure out all that information that we're given. We're told that X is going to be a random variable of the number of rounds that misfire, that X is going to follow a binomial distribution with N equals 3, and the probability of a misfire is 0.1. Now it asks, why does it follow a probability, a binomial distribution? And we'll have to say that the trials are identical. They're just firing it. We assume that the bullets are independent. I assume that they're bullets. They're calling them rounds, so I'll say rounds are independent. These are just kind of keywords. Identical, independent, which means that the outcome of one round does not affect the second round, etc. So just because one bullet misfired doesn't mean it's going to cause the second bullet to misfire. And identical, independent, and the outcome of each trial is either a success, in this case it's a misfire, or a failure. And in this case, it would be a fire then. And so that's all that you need to say for part A. And then the next one, it says B. We're asked, calculate the probability of x equals 1. So what that's actually saying is what is the probability that the number of rounds that misfire out of 3 is 1? Okay. Now we need to remember our binomial distribution formula. This is not given on the final exam. You have to recall this. But in general, what we have is the probability of there being, say, x misfires, okay, is out of the total number of n rounds, we want x number of successes, multiplied by the probability of a success, and this is going to happen x times, and out of those remaining, we have the successes, it's going to occur x times, which means that so this is the success, and in here this is the failures, and these are going to happen n minus x times. So in our case, the probability for us is x, but we also know that n has to be 3 because that was the total number of trials that we had in total, so it has to be 3 for us. So this is just our general formula. I have 3 choose x, then multiplied by the probability of success, which was 0.1 right here, to the x. And then I have the 1 minus p, so that would be 0.9, and then 3 minus x. So I'll just use this. So now I substitute in for x equals 1 right there. So I have 3 choose 1 multiplied by 0.1 to the 1 multiplied by 0.9 to the 3 minus 1. So that gives me 2. Number of ways that I can pick 3. So I have 3 items. I'm going to pick one of them. There's 3 ways to do that. Multiplied by 0.1. So 0.1 to the 1 is 0.1. Multiplied by, I have 9 squared, so that's going to be 81. And then I have a 0. So it's going to go over 1, 2, 1, just once there. So 9 squared. Oops. Good. Okay. So when I multiply that, I have 3 times, and that moves that over once. So I got 0.081. And then multiplying this by 3. So that's 81 times 3. 3 times 24. So I got 0.243. So again, this is a very simple, straightforward calculation. Something that we expect you to be able to do. Let's see, and then the last one. Okay. The last question says, show how to compute the probability of 1 less than x less than 2. So here's C. What we're asked is the probability of 1 less than x less than 2. So that's equal to the probability of, well, what are the values between x, 1 and 2? Well, it's just x equals 1 plus the probability of x equals 2. And then I use my formula again that I had right over here. So, but I've already calculated all that work there, so I'm not rewriting that all out again. So I would write 0.243, so that the only thing I have to calculate now is just the probability of x equals 2. So that's 3 choose 2 multiplied by 0.1 to the 2 multiplied by the probability of failure, which is 0.9, and then I have 2 trials that are going to be misfires, and that means I'm going to have 1 trial out of the 3 that are going to be fired. So there's 1 that's fired. So I get 0.243 plus, and that's 3 choose 2. And this is why Pascal's triangle comes to save the day. I don't want to have to do that formula. So and 0. This is 0, 1, 2. So this is the number I want. So it's 3 times 0.1 squared 1, there we go, times 0.9. Okay. 243 plus. I'll do the 0.01 here. I'll do the 0.9 times 3, which gives me 2.7. And then when I multiply this by 1, I'm going to move it by 1, 2, yeah, 2 decimal places. So I have the 27. So 1, 2. So there was my 2, 1, 2. There we go. Put that dot in there, and then I add that in. So that gives me 0.27. And I'm done. I've done that question. So if you noticed, this is very typical of what we would expect. You would be able to compute this quite easily. B was just some simple arithmetic, and you know, I didn't even bother using the real formula for 3 choose 2. I used Pascal's triangle just to calculate 3, and it was just a matter of just kind of moving some decimal places around. Okay. The last question, number 11, it says you don't have to be, you're not responsible for it. It's something that we didn't cover in class, so it's not on the final exam. Okay, so I've gone over time. It's actually almost 9:30. It's 2 minutes away from 9:30. So I hope that I was able to explain everything very clearly and using different techniques, using visual and a visual approach, a mathematical formula approach. So there's lots of ways to do a problem. And as long as you're telling me what you're doing, why you're doing it, it's good. It's, you know, and if you made a mistake, something like you mixed up thinking that it was order matters, but it really didn't matter, we're not going to ding you as much marks as if you didn't tell us what you were doing. So again, the more you explain to us what you're doing, the better that we're going to be able to understand what you're saying. And balance that with how many marks are given for each of it. If, I ask, when we're asking about the binomial, why is something a binomial distribution? Why is it following a binomial distribution? There was those 3 key points. We just wanted that it was identical trials, that the outcomes were binary, that there's a success or a failure, and that the trials are independent. You don't have to tell us too much more about that. So, just balance with what is given for the marks and give us enough idea of what you're doing. Okay, so that was very exciting. I hope that everyone was able to follow along, and I wish you all the best of luck on your final exam. So 9 a.m. on Friday, the 14th of December. It's 3 hours, and take your time. There's going to be enough time, I think, for everyone to finish that exam. But just take your time and write out everything and give us explanations. Okay, good night.